In this video, I want to talk a little bit about logistic regression, uh, simply because it's the thing you're most likely to run into in the context of machine learning than anything else, I suppose. So, the first major difference is linear regression is a regressor. You get a continuous outcome. You add all the features together, you get something continuous at the end, and then you use a threshold to decide, or in order to discretize it, or in order to make it binary. So that's why we have something like 0.5 or 0.7 becomes a cutoff point, or becomes a threshold. Because we're turning a linear into we're turning a regressor into a classifier. Logistic regression, on the other hand, is only a classifier. It doesn't have a regression option. And what it does is that it calculates the log odds ratio of membership in a class, and then you just compare which of the different classes has the highest number, and that's the label you give it. So while the linear regressor might say 0.46 survived, that means died. Logistic regression would instead say there is a 0.48 died, a 0.51 survived, therefore survived. It's not super important to know exactly what a log odds ratio is. Just think of it as a kind of probability. But I do want to show you, to give you a little bit of intuition for what it is, or what the differences are. So, looking at a linear regression, you've got an intercept at beta naught, you've got beta 1 as a weight, you've got your predictor. This is all just like Algebra 1. I'm sure you remember it from middle school. When the intercept increases in a linear regression, the line just goes up. Are you predicting that, or how many cakes is someone going to buy? If my intercept becomes 3 instead of 1, I'm just giving everybody more cakes. Now, when we change our beta weight, we just get a steeper slope. So, it's not, instead of saying, oh, everybody gets more cakes, it's people who like chocolate more are going to buy that many more cakes for each extra level of chocolate liking they have. Logistic regression, on the other hand, a little different. I've put the formula over here on the right. You do not need to know this. But this is where it comes from. And what it does is it gives us a curve that asymptotically approaches 0 on one side and asymptotically approaches 1 on the other. It's got a 0.5 is where it will, by default, cross. And the scale is a little wonky. But this is our way of classifying things probabilistically. We'll be able to say, hey, what are the odds that someone right here is going to survive? Well, I'm just going to look up and say, oh man, that number looks like a survive. What are the odds on this fella? Not so hot. So how does this transform? Adding to the intercept moves the curve left and right. So now, instead of someone with a value of 0 being the one with a 50-50 chance, this is someone who has a prediction of -2 or negative something, it's actually almost certainly not 2, we'll have our 50-50 chance. So that means our person who has a 0 in the trait is now pretty likely to survive. Or whatever it is we're trying to predict. And it is important to note that it moved in such a way that for a given prediction, for a given feature value, your prediction will be higher. So that's what a positive 2 is. It winds up doing that by moving the 50% threshold to lower to the negative, but that's just the curve moves to the left, which means for any given value, your prediction is higher. Now, how does it work when you change the slope on something, or the coefficient? Well, a higher coefficient makes it steeper. So it gets closer to being a straight up and down line, so every little bit of improvement makes you go up more. However, it still just goes on asymptotically towards 1, and down here asymptotically towards 0. So we've still got a maximum of 1 that can be predicted, and a minimum of 0. It's just the transition is over a shorter range.